Welcome back to Mad Medicine. In this video, we're going to be discussing metaplasia, which is one of the cellular adaptations you need to know for medicine, for the basics of medicine. Now, if you haven't already done so, don't forget to subscribe to our channel because your support really means a lot to us and it really helps us out with growing our account and also exposing our account to other individuals who could find this free content helpful for their studies. So with that being said, let's discuss cellular adaptations because you have to have a better understanding of these adaptations in order to understand metaplasia as well. So one thing to remember is that our cells are constantly under a lot of stress due to the environment that they are in. And one example of this is the stomach lining. Our stomach lining is constantly being exposed to our stomach acid, which is primarily hydrochloric acid, which is a very strong acid, and that acid is able to erode our stomach lining, but our cells have adopted ways to get around that stressor so that they survive. Now, our organs are generally in a state of homeostasis, meaning they're able to support any sort of stress that's being placed upon them to a limit, and after that limit, they're going to either develop a adaptation mechanism to grow, or they're going to undergo damage. Now, the change for the organ itself is going to be based off of the type and the severity of the stress that's being placed upon it. And an increase in the stress is eventually going to lead to a growth of the organ. And that can be done via two main types of growth mechanisms or growth adaptations. One is hypertrophy, and the other one is hyperplasia, both of which we have discussed in our hypertrophy and hyperplasia lectures. So you should definitely check that out on our account. Now, if the stressor goes away and there's no need for growth adaptations to occur, atrophy will undergo, and our cells will actually undergo atrophy, or our organs will undergo atrophy in order to allow the organ to return to homeostasis, like we said right here. So if you grow, it's because there is a stressor, and when you take away the stressor, our organs are going to go back to the normal resting state. And that is all very important to understand because it gives us a good understanding of how our cells and our organs are able to adapt to different types of stressors. Now, our organs can also adapt to stress via metaplasia, which is a different type of adaptation than the ones that we have discussed thus far. So let's talk about metaplasia, which is the topic of the rest of the video. And you need to understand metaplasia really well because this is going to set up essentially our foundations when we discuss dysplasia and cancer. So metaplasia is a transformation of one differentiated cell type to another type of cell. So when you go from, let's say, stratified squamous to stratified columnar, or from a columnar to a squamous cell, whatever different type of cell it becomes, this is a type of metaplasia. And usually a change in the stress of an organ is going to lead to the type of cell being changed. So the type of stress that's being placed on an organ, if it changes, our cells and our organs have adopted ways to change the cells that are within the organ to essentially be able to maintain their function while still accommodating the stress that's being placed upon them. Now, this is usually going to occur via cellular reprogramming of the stem cells, right? So once a stem cell has become a specific type of cell, there's no way for that cell to essentially change. All of this is going to happen actually at the stem cell level that is, allowing our cells to regenerate the cells that are lost. So the stem cells are going to be reprogrammed after a continuous amount of stress being placed upon the organ. And most commonly, this is going to involve surface epithelium. Why is that the case? Because the surface epithelium, number one, is a very, very rough environment. It's a very stressful environment for the cells. And number two, you have cells located in the basal layer of the epithelial lining. Usually they're present, so you're gonna have easy access to stem cells, which are gonna be able to be reprogrammed to produce a different type of stem cell or a different type of cell later on. This is due to the most common site of also environmental changes that occur, right? Because that area, the surface epithelium, is what's interacting with a plethora of different compounds, a plethora of different environments as well. So it has more chances to change, more chances to undergo metaplasia. Now, metaplastic cells are actually designed to better adapt, to better handle the stress that they're being placed under. The reason why you're going to undergo metaplasia is not because of some willy-nilly process. No, it's going to happen because some change in the stress that was previously placed upon an organ is going to need a different type of cell. And we're going to discuss an example of this in a little bit. But understand that these cells, the metaplastic cells, are often better adapted to handle that stress than the original cells. And if the organ does not undergo metaplasia, the organ might actually become damaged based off of the original cell type that's present with the change in the stress. An example of this is Barrett's esophagus, and this is a classic example that you need to commit to memory. It's really high yield, so we're going to put this HY next to it so you guys remember. So in Barrett's esophagus, you're going to have metaplastic changes that occur in the mucosal cell lining of the lower portion of the esophagus. The lower portion is very important because that's the part that's constantly being affected in Barrett's esophagus. Now, normally, that lower portion of the esophagus is actually stratified squamous epithelium. So it's just going to be this thin layer, right? It's going to be stratified and it's going to be squamous cell. Now that is the normal presentation. Now this is going to be converted into columnar cells, right? Like this, simple columnar at that, in order to accommodate the stress that's being placed upon them. And these columnar cells are going to have goblet cells interspersed within the actual thing. Now, normally, this type of presentation, this is a simple columnar, and the interspersed goblet cells is only present in the small and large intestines. And there's a reason why it's only present there. And this is all because of constant GERD and constant reflux or gastroesophageal reflux disease. In this condition, you're going to have constant exposure to an acidic environment, right? So hydrochloric acid, which is the main compound or the main acid in our stomach acid. That compound usually goes from our stomach. So let's say this is the esophagus. It usually goes from our esophagus to our stomach down to our intestines, right? That's the normal presentation that occurs, a normal cycle in terms of our human body and the pathway for stomach acid to go down. But in GERD, you're going to have reflux. So instead of it just going down, it's also going to go up. Now, remember, we said that the goblet cells and the simple columnar epithelium is more so common in the small and large intestines. And the reason why is that this presentation, goblet cells and simple columnar epithelium, is well adapted to handle a more stressful environment, like in the hydrochloric acid that's present in stomach acid. So when that stomach contents get emptied into our intestines, our intestinal epithelial layer, which is primarily composed of simple columnar epithelium, is going to be able to handle that stress. Whereas when you have GERD, that stomach acid is being refluxed backwards into the esophagus. The stratified squamous epithelium is not well adapted to this type of stress. So it has to undergo metaplasia. It has to go from stratified squamous to simple columnar in order to handle the increase in hydrochloric acid that it's being exposed to. Otherwise, you would have erosion of the esophagus, and that could lead to ulcers and even perforation. Now, the columnar cells, like I said, are better suited to handle this acidic environment. That's why they're present in the intestines, and that's why metaplasia occurs in the esophagus in the case of Barrett's esophagus. Now, if left untreated, and this is very important, if left untreated, Barrett's esophagus can progress to esophageal carcinoma, and that is one sequelae of metaplasia you need to understand. Metaplasia can often lead to dysplasia and cancer if left untreated. We're going to talk about that more as it comes along later on in this lecture, but you need to remember this main key point, this main fact, because you can get tested on what is a precursor lesion to esophageal carcinoma. Or in a question stem, the question will present a patient who has long-standing GERD, who presents with a endoscopic finding of Barrett's esophagus, and the question might ask you, what type of cancerous lesion is this patient more predisposed to based off of the clinical presentation? And the answer is going to be esophageal carcinoma. So you definitely need to remember this. We're going to put a HY next to it as well, so you remember this is high yield. Barrett's esophagus is also going to be discussed, in our GI modules as well in more in depth, but it's definitely a concept that is very high yield. It's definitely a concept you need to remember and you cannot forget for your examinations. And this is what a histologic slide looks like for Barrett's esophagus. As you can see, this layer right here is your stratified squamous layer, right? You can see the stratification right here, this full thickness stratification, and you can see the squamous cells being lined up next to each other like that. This is normal. This is how your esophagus should normally be. And on this side, we can see where you have the simple columnar and the goblet cells. And you can see that if you had zoomed in, if we were able to zoom in more, it's kind of hard to see in this photo, but you can see these are more columnar than they are stratified or squamous even. So this means that you have metaplasia happening here, which is abnormal. And this is a sign of Barrett's esophagus. Okay, so you need to remember this. If you see some side like this, they are showing Barrett's esophagus. And hey, what is this? What can this be? What can this lead to? Esophageal. I'm gonna write this so you guys can see it over and over again to commit this to memory. Esophageal carcinoma. Okay, so I think we've covered Barrett's esophagus in terms of metaplasia pretty well, and we're going to move on. We're going to talk a little bit more about metaplasia. So metaplasia is actually reversible, and that's very important to remember. Unlike different types of lesions that can occur like cancer, which might not be reversible, metaplasia is a type of lesion that can be reversed if you remove the stressor that's being placed upon the organ. So in the terms of Barrett's esophagus, if you remove the reflux of the hydrochloric acid that's affecting the lower portion of the esophagus, you are going to actually go back to stratified squamous cell epithelial layers in the esophagus. And you can do that by treating the GERD, right? Whether with a proton pump inhibitor or other types of medications. But if you remove the stressor, you're going to go back to the normal cell type. But if it's not removed, if you do not treat the metaplasia, if you do not control the underlying cause of the metaplasia, it can proceed to dysplasia and even lead to cancer. That is very important. This is pretty important, so we're going to put HY next to it so you don't forget this. Metaplasia can lead to dysplasia and cancer. And the example, again, is Barrett's esophagus going into esophageal adenocarcinoma. Now, apocrine metaplasia. Apocrine metaplasia is not going to lead to cancer, and this is important. This is, I guess you could say, the exemption to the metaplasia rule. Apocrine metaplasia is actually a reversible type of transformation that occurs to an apocrine phenotype, okay, to a cell of an apocrine phenotype. And the most common is going to be fibrocystic changes that occur in the breast. In this case, fibrocystic changes that occur in the breast are not actually going to lead to cancer. It is a metaplastic change that occurs in the breast, but it is not going to lead to a breast cancer. Just like how we discussed in our previous hyperplasia lecture, in the case of benign prostatic hyperplasia, that type of pathologic hyperplasia is not a precursor lesion to cancer. It is a benign pathologic condition. Same thing with fibrocystic changes to the breast. This type of apocrine metaplasia is not going to lead to cancer. The other example of metaplasia that you need to know about is vitamin A deficiency. Vitamin A deficiency can lead to metaplasia because vitamin A is very important and is necessary for the maintenance of our very specialized tissue. For example, our eye. In our eye conjunctiva, the vitamin A plays an important role in maintaining that tissue. And a lack of vitamin A can lead to keratomalacia. That is very important to remember. Keratomalacia is going to be caused by low vitamin A levels, okay? And this is a type of metaplastic condition that occurs in the eye. And this is what it looks like. This is what keratomalacia looks like. You can see this keratinized layer right here, and you can see this white milky area. That is keratomalacia. That's a classic presentation, and you need to know it is happening because of low vitamin A levels. Another example of metaplasia is mesenchymal tissue. Mesenchymal tissue can also lead to metaplasia. And the classic case is myositis ossificans, which you can see right here. You can see this calcified mass within the left hand between the thumb and the first digit, okay? You can see it right here. This usually is going to occur due to trauma to skeletal muscle. And when you have the trauma to skeletal muscle, you're going to have inflammation. That inflammation is usually going to occur during healing, but it's going to lead to metaplastic production of bone instead of the skeletal muscle that should be happening. So what ends up happening is that inflammation can change the stem cell type, and this can lead to bone production and calcification within the skeletal muscle. That is a classic case of myositis ossificans, which is definitely a type of metaplasia. Now, this is going to look very similar to osteosarcoma, but it does not grow off the bone. And if you look very carefully, you can see there is a clear demarcation between the actual lesion and the bone itself. And you can see this black line right here, which is showing there is no connection between the bone. Same with this bone right here, there is no connection. Therefore, this is not osteosarcoma. Osteosarcoma is going to grow off of the bone. So if this was your digit, right? Your proximal interphalangeal digit, it's going to be something like this. This would be a sign of osteosarcoma, meaning it is growing off of the bone itself. Whereas this is more so, this is your digit, right? And this is the lesion growing off the bone. So this is how you can differentiate between osteosarcoma and myositis ossificans, along with the fact that you have some sort of trauma. Usually it could be an injury that occurs to the hand, an insult that occurs to that skeletal area. And with that being said, that's everything you need to know about metaplasia. We covered several topics in this video, so make sure you understand all of them, and make sure you understand the clinical correlations between Barrett's esophagus, between myositis ossificans, between keratomalacia, and their role in metaplasia, and how metaplasia plays a role in those disease presentations. Don't forget to subscribe to our channel, because your support really means a lot to us, and it really helps us out, and we really appreciate it. Thank you.